Okay. So I think this is, how these people think of this stuff, I have no idea. That's the guys that are geniuses become comparison to everybody else. This guy Dalton, for instance. We're still following what he says, right? That at the fundamental nature, you've got atoms, and they're combining and doing chemical reactions, and you have elements, but everything has this atom idea, right? The smallest particle. Except we've kind of gone on a little bit further now. Notice what he says, it's impossible to create or destroy a particle of hydrogen. Well, if you kind of read the news a little bit, there's a particle accelerator, right? These things are so expensive that nations got to get together to each fork in some money, right? Well, we forked in some money, but not a whole lot, and the physicists weren't so happy about it. But anyway, there was a small minority of physicists in the world that said, do not turn this thing on, because we're blasting these things apart to see what's inside them. And they're looking for the Holy Grail, or the God particle, it's called. It's supposed to hold all matter together. And Higgs particle. But the point is a small minority of physicists said, don't turn this thing on. You could create a black hole, a miniature black hole, and it's going to cause some major problems here on this planet. So it's just a minority of folks, right? But still, these are guys who are educated. So it kind of did concern me, right? Are you guys going to flick the switch? But the far majority of everybody's saying, oh, come on, nothing's going to happen, nothing's going to happen. So they flick the switch, and they're doing the experiments, and no black holes. So that's good, right? But so Dalton was a little bit off, but we're still using his ideas. For example, precipitation, that's something that's way ahead of us, but let's see if this is going to work. Here's a movie of a reaction, and it's using atoms. And exactly what's going on here isn't...
In this animation of a precipitation reaction, the silver ions, shown in gray, and the chloride ions, shown in green, are active participants in the reaction and combine to form the insoluble silver chloride crystal.
So all I'm showing you this for is it's full of atoms, right? You have these little guys floating around. These are supposed to be what compound? You recognize it? It's bent, has H2O, right? That's water floating around. So this whole thing is going on with water. And you have this solid forming, okay? But it's all atoms, right? Some atoms combine to make molecules and compounds and all that kind of stuff. So, how did he figure that out? I don't know, right? That takes quite an imagination or a lot of experiments or something. He made a big leap, but he's right. So, Sydney, what is the difference between an element and a compound? Yeah. Okay. You're close. This, I would call this molecule, sorry. This is that stuff you used in lab yesterday. If you had lab with me, it burns natural gas. You can't smell it. They add those sulfur compounds so you can smell it. But this is a molecule of methane. Carbon in the middle, all these hydrogen atoms. This, anybody, would be an example of a what? An element or a compound? Compound, right? So the carbon surrounded by 4 hydrogens. How about this? Pop one up. There it goes. Hydrogen, hydrogen, Manuel. What is that? Element. It's supposed to be a trick question, but he got it, right? Because it's the same. This is how hydrogen, the element hydrogen, exists in nature. Okay, good. How about this? What would you call this, Giselle? So this guy's flying in the air, this guy's flying in the air. I'm not sure how this occurs, but they collide, they rearrange. Yeah, it's going to happen a lot faster than this, obviously. There, chemical reaction, right? So that's I think you got a handle on that. The periodic table, all the elements known to mankind, right? Some terminology in the periodic table. Let's do this a little more random-like. Oh, Stephanie, Where are the groups in a periodic table? Where are the groups? Good. They're the vertical columns. So these are the groups. And I'm just going to mark the ones that we need to know. Those are the ones that we need to know. Okay, and we'll get to that. So groups are vertical. And the reason why they kind of say, okay, groups, they all have similar chemical properties. And it gets more violent as you go down. They get more reactive as you go down. And we'll have a little example of that. But well, that's coming up next. How about periods? What's a period then, Tanya? Yeah, good. Horizontal. So there's a period. Period is the horizontal. Okay. Groups going up and down. For example, let's take a look at rubidium reacting with water and cesium reacting with water. So what are these? Here's rubidium, here's cesium. The same group. But as you go down, remember things get more violent, things get more reactive. So let's take a look at rubidium with water first.
Was that it? Don't think I needed my safety screen.
So there's rubidium. Now let's check out cesium and water.
Okay, everybody, be careful. So we have our cesium under oil. We now need to lift it up using the new device and then drop it in the water. And let's see what sort of chemical reaction it does today. Everybody ready? Neil? Well, quite a spectacular reaction. As the cesium reacted with the water, gave away its electron, off she goes as cesium plus.
So a little more interesting as things get more violent, I guess, right? A elements. So, let's see. So anything with an A on it, I guess it's just these guys. They're called the what group elements? Starts with an M. Does anybody know? Main. Good, main. And we haven't started talking about ions yet, but the point is the gentleman, the British guy, he kind of gave us a hint. Things giving away electrons. So the point is they form ions. And for example, the cesium, it only has one electron that it wants to give away. So all it can be is cesium plus. And that's getting way ahead. So don't really worry about it. But the point is these main group elements, their charges are fixed for ions. And when we get to that point, that'll be really helpful, because this will be a really good cheat sheet, so you don't have to memorize anything. You know that cesium is always +1, because you just use a cheat sheet, use a periodic table. And I don't worry about it when it comes, though. The B elements are referred to as blank metal elements. Starts with a T. Transition, good. Transition. And their charge isn't fixed in forming ions. So they could be, like you could have copper plus. You could have copper +2. You could have copper +3. There's a number of possibilities. So again, we'll worry about that later and how to name them. Here's the names that I was talking about. I said that we need to know the names of the following groups, right? Need to know the names of this group, this one, and this one. So that's 1A, 2A, 7A, and 8A. Okay? So group 1A. Ashley, you know what that is? Starts with an A. I don't know if you're going to know this. It's probably in the reading, but if you got it out. Alkaline earth. Alkaline earth. 2A, this group right here, is just alkaline. What does the word alkaline mean? Anybody know? Means basic. It'll be basic. 7A, this group right here, starts with an H. Halogens. Somebody remembers or read it. And then the last group way on the far corner, not supposed to react with anything, although some of them do. Starts with an N. Noble gases. Extremely stable. That's why they won't react with much, including themselves. Okay, now it starts. The naming. Know the names and symbols of all elements in the first 4 periods of the periodic table. Let's try a few. So what I'm saying is in the upcoming quiz, I could say, okay, Na, spell it. Sodium, S-O-D-I-U-M, right? That kind of thing. Or carbon, it has what element symbol? C. So you have to know them both ways. So let's just start up here. Let's start with, I don't know, Kenneth, and see if you can name these, right? Hydrogen, Lauren. Helium, good. Audrey. Lithium, Kendall. Beryllium. Now spell beryllium. You get brownie points if you can spell beryllium. B-R-Y-L-L-I-U-M. Right? So spelling counts. Where are we at? Okay, B. I guess I'm with Stephanie. Boron. And then Kenneth. Carbon. Sarah. Nitrogen. Oxygen. Rebecca. F. They put this in, when I first moved here, they didn't put this in your water. And I was really upset about it. Fluoride. Because, really upset about it because we had a little baby. And we had to break those little fluoride tablets and give it to him. And we could overdose that little kid, right? You don't break the stupid, it was really stupid. San Antonio is one of the very few cities that didn't fluoridate their water. But now we do. So, okay, fluoride. N-E, Mia. They have to make the signs out of this gas. Neon gas. Neon. L-I. Connor. Oh, did we read that one, did we? No. Oh, Na. Sodium. Magnesium. The cans. They make the cans out of this. Aluminum. This valley. Megan. S-I. A lot of computer stuff. Wafers. Silicon. Okay, silicon. P. Bowdy. Phosphorus. S. Manuel. This stuff stinks. This is what they put in that methane to make it stink. This is what makes your sulfur, your you-know-what, stink too. Cl. Chloride or chlorine. Chlorine would be best. Chlorine. Ar. This actually isn't air, like 1%. Argon. Lorena. K. Potassium. Ca. There's a lot of this in our water since we have an aquifer. It's dissolved. Calcium. Oh, I don't know if you know this one. Scandium. Good. Kenneth. Ti. They make really expensive golf clubs out of this. Titanium. Lauren. This is in vitamin pills, but you have to read the little small print to see it. Vanadium. Audrey. This is also in vitamin pills. Chromium. This too, Kendall.
Hold on.
MN.
Magnesium and then I can spell it.
Spell it.
M-A-N.
G. Yeah.
G and then it's like E-S.
No, you're so close.
A-S-E.
She's trying to say manganese. Manganese. So manganese, magnesium. Manganese, magnesium. Fe, iron. Cobalt. Ni. They're worth 5 cents, but they don't make it out of this. Nickel. Cobalt is CO. This one is copper. Yeah, isn't that weird? Why there's no U in copper. All right. It must be some British thing or something. Right? Okay. Zn. Rebecca. Zn. There's not very many that start with Z. Zinc. Mia. This is gallium. That's that's really rare. You're not going to see that one very often. Back up to front. Bowdy. We're after gallium. Another one that's not very common, except probably in the computer industry for doping and that sort of stuff. Germanium. Okay. Now, Megan, if you want to kill somebody, you could use this. It's AS. Arsenic. An assassin will use arsenic. SE. I think kind of like there's a singer, not Selena, but selenium. BR. Bromine. Bromide will be the ion. So bromine. Last one, Connor. KR. Superman. Krypton. Krypton. Okay, so know the names and symbols of those first 4 periods. Okay. Nuclide symbols. So what we want to do is be able to write the symbol to describe an atom, right? You would think, like, this is supposed to be an atom. You think we could just write H, right? Because it's supposed to be a hydrogen atom. But they want more information, because not all hydrogen atoms are identical. They're supposed to be, aren't they? Isn't that the whole idea of an atom? That's the idea behind an atom. They're all supposed to be identical, right? But some are a little bit heavier than others. So what's making them heavier? Something in the nucleus, you have a little bit more of them. But all hydrogen atoms do have the same number of something. And that's what we're getting into is the difference between these two numbers, atomic number and mass number. The atomic number is really the identifier. The atomic number is the number of what in every nucleus of that atom, number of protons. The atomic number is the number of protons. That is what determines, that and only that is what determines the element. Determines the element. Right? Because that's the element symbol. Like H for hydrogen or C for carbon, all those that we just went through. So electrons doesn't matter. Only the number of protons determines what the element is. Well, what else is left? There's an N, someone said it. Neutrons. Just this subatomic particle that has about roughly the same amount of mass as a proton, but no charge. And we'll talk about later what they're doing there to make things stable. As things get bigger and bigger and bigger, you need more and more neutrons. Otherwise, the thing's going to fall apart and it gets radioactive. So atomic number is the number of protons. That's what determines the element. Then what the heck is the mass number? Protons plus neutrons, exactly. So that's protons plus neutrons. So you could have the exact same element, right? Whole bunch of hydrogen atoms, but some hydrogen atoms could have a little bit more mass than others. Now, they all have to have one, according to hydrogen. Where do you get the atomic numbers? I'm kind of jumping ahead. On the periodic table, where do you see these atomic numbers? Yeah, they're the blue ones, the right corner. The whole numbers, right? The whole numbers, because you can only have so many protons. So every single hydrogen atom has to have one proton, but some weigh more than others. That means in their nucleus they must have more neutrons. So how do you write symbols for those and describe the difference? Right here, right? You'd write H, you'd write a 1 down here, right? And then, I don't know, if you write a 2 up there, well, that means that there's one proton and one neutron. If there's one proton and 2 neutrons, you'd have to write a 3. Okay? But there's always one proton, otherwise it won't be H. So these, what I really want to hit on is these two have to match. Whenever you have calcium, for example, you better have how many protons in there? What little subscript? A 20, right? If you ever see a 20 as a subscript, what does the symbol have to be? Ca. So this number up here can be whatever. It's just, you don't know, right? It's protons and neutrons. But the periodic table will give you these two at least. Okay. Nuclide symbols are named with the convention, the element, and then the number, where the number is the atomic number. Okay. For example, name this nuclide. Oh, Kenneth, what's Cl again? Chlorine. So I guess you would read it as chlorine 35. All right. Oh, I added this morning. Sorry, I added this morning because I didn't think it was hit strong enough in your stuff. So I just added it this morning. Sorry. You get what you pay for. Okay, so chlorine 35. So that would look like this with what number down here? I don't have this memorized. Where's chlorine? There it is, 17. All right. So this would be the symbol. Okay. And this is how you would name it, chlorine 35. So that you just say the element name and then the mass number. Okay. Write down your answer for this one, for part A here. What is the nuclide symbol for the nucleus that contains 14 protons and 14 neutrons? Then go ahead and name it. Write the nuclide symbol. So when we say nuclide symbol, we're talking about this format. All right? Give the element, and superscript is the mass number, subscript is the atomic number. The nuclide symbol for nucleus that contains 14 protons and 14 neutrons, and then go ahead and name it. So Emily, how did you answer this? Okay, what's the symbol? Si. Okay, then what'd you do? Oh, they're both 14, ain't they? I should change that. Because it's hard to screw up, right? Okay. Oh, yeah, thank you. There is something to do, isn't there? You got to sum them up. Thank you very much. How would you name it? Silicon 28. Or spell out 28 if you want. Okay. Fractional abundance. The atomic mass of an element is the number located below its atomic symbol in the periodic table. What does atomic mass represent? So look at some of these. We already, pick on carbon. If you have a carbon, it has how many protons, Lauren? Carbon has how many protons? 6, right? Then there's this number beneath them, 12.0107. They all have this number beneath them. And they call that the atomic mass. So I guess it should be grams. They don't, but what does it mean? So you literally go out into nature, right? A tree or whatever, or the ground or whatever. You get your source of carbon, just in nature, how it naturally exists. Are all the carbon atoms identical? No, because some have more neutrons than others, right? That's the whole nuclide symbol idea. But they all have how many protons? 6. So we've got some fancy equipment upstairs that can actually do this and identify these atoms, right? But this is what's kind of strange, I think, is in nature, when there's a natural ratio for these different isotopes to exist. For example, you've heard of maybe carbon-12, or maybe heard of carbon-13 dating, right? So what they do is they know that, I don't know what the percent is. I should have Googled that before this. Let's say when this tree is first grown, right, that in nature there's 25% carbon-13. But carbon-13 decays to carbon-12, and it takes 1,000 years. So they figure out, they go to this really old tree-looking thing, or petroglyph, or a rock, or whatever that's petrified, and they identify how much carbon-13 is left. Wow. That means it had to, because they know it started out with this amount of carbon-13, so it's very easy to calculate how long it took for it to decay down to this ratio. So how does that fit with this whole atomic mass idea? Well, you need to take this many atoms, collect that many atoms. It's a lot, right? But it's a lot. You collect that many atoms of that element. So if you're talking about carbon, they all had better have how many protons? 6. So everything with 6 protons in it. You collect 6.022 to 10 to the 23rd atoms of this in nature. Doesn't matter, right? There'll be their natural ratios and abundances and everything. You collect that many. And then what's their mass? There it is. 12.01 grams. Well, 12.0107 for carbon. So it takes into account all the carbon-13s, all the carbon-12s, even though they're a little bit different in mass. So that's why, one reason why it's not exactly a whole number, because you have these different isotopes in there. So it's just a natural collection of things. And the reason why I'm talking about that are these types of homework questions. So, and this is a very fundamental idea, but calculate the atomic mass of an element with 2 naturally occurring isotopes. So here's one isotope. 62.93 is how much it weighs. 64.928 is how much another isotope weighs. And here's how much it exists in nature. So about 70% of X63 and about 31% X65. So X is what we're trying to figure out. What element is it? Well, you can pretty much guess. I mean, what the heck is around 63? Copper. So odds are the answer is going to be copper, right? But the point is this is what these machines do. They analyze, they figure out what the mass is, the fingerprint. They figure out the masses and the ratios of them, and you can figure out what the compound is. Take this type of instrument out into the jungle, right? I don't know, Indian Joe has been eating this funky-looking purple flower, and he knows when he eats it, his, I don't know, it heals really fast after a little tiger gouges them or something, right? I'm just making this up. But the point is they know that, wow, this little purple flower works great. So you work for a company, Advil or whatever. You go down to the jungle. You get some of that purple flower. You extract all the different compounds in that purple flower, put them in this machine, and it tells you what those compounds are by doing just this, figuring out the masses and the ratios. So you're not doing something near that complicated, but that's the exact same idea. You're just figuring out what element it is, magic-wise. So how do you do it? Pretty much, if it is copper, the atomic mass had better come out to be what? Audrey. If it is copper, the atomic mass had better turn out to be what number? That's the atomic number. That's the number of protons. The atomic mass is the mass of the whole atom, 63.546. So we better get 63.546 if it's copper. How do we do that? Pretty much all you do is you multiply the mass times its fraction. Write it over here. The mass times its fraction, write it over here. Add it all up and see what you get. It has to match something on the periodic table. So try it. Multiply them, add them up, see what you get. So the name of the element must be, how do you name it? Copper. Right? Copper. What is the name of the element? Copper. Because that matches copper's atomic mass. Okay, so that's how you play that game. The computer in the jungle is doing these exact same calculations, except it has a lot bigger library than that periodic table. Okay, in its computer. Okay, so I don't think you have these. I wrote these down because I figured we were going to get done a little bit early. I don't want to let you go early. You're not paying to get out of here early, right, Kendall? So let's try some of these. Right? Write down your, we can go to the boards. Let's go to the boards. It's a good time to go to the boards. Right? We got a little bit of time. Let's go to the boards and finish these three out, and then we can call it a day. So we've got an extra board over here. We've got one over here now. I think we need an eraser over there. Chalk, steal an eraser and put it over there. So you can use these side ones, then you have to be bunched up so much. There's a side one over here and a side one over here. So let's try this first one. What is the nuclide symbol for the nucleus that contains 20 protons and 21 neutrons? Yeah, this one's so much longer. Right, the nuclide symbol so everyone write down their own answer.
Okay, thank you.
Just don't copy off of Megan over there. All right, so you got it? Everyone agree? So 41 should be the superscript, right? 41 and 20 in the bottom. 20 is calcium. Does everybody agree? Mm-hmm. All right. And how would you name it?
Calcium 41.
Calcium 41. Try the next one. Oh, heck, I just do it this way. It's easier. Right? Try EX4. Anybody need some new chalk? You have to scratch your fingers. I know. But you have the lab. All right. So then the next one is 17. Hopefully the element everybody wrote is chlorine, right? Is that 34? 17. And you'd name it. Probably the easiest way is just this, right? Cl-34. Okay. One more, then I'll let you go. Calculate the atomic mass of this element and identify it. Identify what the element is. If you're not sure what to do, just ask. So you should have two answers, right, when you're done. You need to report the atomic mass and the name of the element, right? Because it wants the atomic mass and the name of the element. So those are the two things you need to report. So the atomic mass, you're coming up with, like what Kendall's got here, hopefully, 24.305 or 24.3, something like that. That's your atomic mass answer. And the element symbol is magnesium. Good deal. So have a good day.
Sir, for the lab, was there anything we had to do for the pre-lab?
There
Just read over it?
is a pre-lab. Let me show you.
Where is it?